Okay, question 19.69, propose an efficient synthesis for each of the following transformations. We're changing the carbon skeleton. We're starting with 6 carbons and we're ending up with 9 carbons. And so what I'm thinking in terms of retrosynthesis is if we could make a cyclohexanone, right, then we could just do a Wittig, right, if we had the right Wittig reagent, right? So we would need what? We'd have this, and then we would need this Wittig reagent to do the Wittig reaction. So how are we going to get from cyclohexene to cyclohexanone? Well, the first thing we'll do is we'll treat it with dilute acid to convert it to an alcohol. Markovnikov addition doesn't mean anything since there's no differentiation between these two carbons. And so we produce the alcohol. Then we can oxidize that. Let's choose a Swern oxidation, so that's DMSO and oxalyl chloride, followed by treatment with triethylamine, and that gives us cyclohexanone. And then we just have to do our Wittig reaction. And again, here it doesn't matter. There's no E or Z to worry about, so nothing to even consider there. So we just draw our Wittig reagent. So we have 1, 2, 3 carbons, and there we go. That's our synthesis. Question 19.69b, we want to go from this geminal dibromo compound. We want to make this acetal. Well, the only way that we know how to make an acetal would be from this ketone and then to treat it with methanol and a catalytic amount of acid and to remove the water. So how do we get from here to this ketone? Well, I think that the first thing we could do if we want to make a methyl ketone would be to convert this into an alkyne. So if we were to treat this with excess sodium amide in the first step, followed by treatment with water, that's going to do a double elimination, and that will give us the alkyne. And hopefully you remember there's a reaction that we can use, which is a Markovnikov addition of water across this alkyne to give us an enol that will tautomerize to give us this methyl ketone. So in order to do that, we treat the alkyne with sulfuric acid, water, and mercuric sulfate, HgSO4. We need to have that in order to get the reaction to work. So we end up producing this enol, which undergoes tautomerization to produce the desired ketone. And then to go from the ketone to the acetal, all we have to do is to treat it with excess methanol and a catalytic amount of acid, and we want to remove the water. All right, in the last one in 19.69, we want to start with cyclopentene, this molecule here, and we want to end up with an 8-membered ring. But something I notice here is that this is an acetal, isn't it? Right? This is just a big cyclic acetal here. So really, I mean, if we think of retrosynthesis, we would make this from this ketone, which is acetone, and our diol would have 1, 2, 3, 4, 5 carbons. So we could say 1, 2, 3, 4, 5 carbons, like that. So 1, 2, 3, 4, 5 carbons, like this. So how could I make that diol, which has 5 carbons, from cyclopentene? Well, I'm going to have to break open that ring, won't I? And the only way I know how to do that is with ozonolysis. So I treat it with ozone, followed by DMS, and that would give me this dialdehyde, where I have 1, 2, 3, 4, 5 carbons, like this. But I could reduce both of those with excess sodium borohydride, and I could do that in a solvent like methanol. So I'll just put methanol here, and that would give me the diol that I want. So I have 1, 2, 3, 4, 5 carbons. I have a hydroxyl here and a hydroxyl here. Now in order to make this 8-membered ring, all I have to do is treat it with a catalytic amount of acid, acetone, which is the ketone we needed, and of course I'm going to remove water, and then we end up producing the desired acetal.